So I mentioned latency previously, and latency is one of the key factors in computer system performance at all layers. Even the latency that it takes to go to DRAM on a single system has an impact on the performance of the system. The difference of being able to fetch a cache line from memory and utilize all the data in the cache line rather than fetching an entire cache line from memory using one element of that cache line and then having it flushed to replace by the next one is a key differentiator in single system performance. So latency affects things inside the box, but also certainly affects things outside the box. So the Transmission Control Protocol, TCP, is widely, ubiquitously used in the Internet. I'm using it now to display these slides to you. This is the thing that we use when we browse web pages, as I'm sure most of you know. TCP provides reliable transmission of byte streams over best effort packet networks. That's a bit of an aside, but the difference in the telephony, the traditional, the telephony network and the Internet and packet switching is the fact that packet networks are best effort. There can be some loss. If statistical multiplexing says that most of the time not everyone is talking at the same time, when everyone decides to talk at the same time for some reason, then some packets are lost, and that's okay. We have to deal with that. TCP is the layer on top that makes sure that those losses are transparently handled and that the bytes go in at one end and they come out the other end in the same order without having been without loss. So TCP uses a sequence number to identify the stream position inside segments, and segments are buffered in the kernel until they're acknowledged at the other end, which is critical for reliability. What this means is that as the acknowledgments come back, yes, I received this packet, yes, I received bytes up to this byte number, then more data can be sent out. So that stream of acknowledgments is used as a clock to drive the control loop of TCP, so these are good things, but what that means is that TCP suffers in the face of latency. So you can see here this sawtooth curve, and what TCP tries to do to take advantage of the bandwidth in the network is as acknowledgments come back and when packets aren't lost, TCP infers there's available resources, there are available resources in the network, and it increases the number of packets that are in flight, called the congestion window. It increases the number of packets that are in flight until loss occurs, and then it says TCP's, the logic is, now there's congestion in the network, I'm sending too much, I'm sending more than the channel capacity, so I will reduce my rate. It's generally called AIMD, additive increase, multiplicative decrease, in that as at steady state, as acknowledgments come back, the number of packets in flight is increased additively. When there's a loss, the number of packets in flight is decreased multiplicatively. So that's what happens with the sawtooth curve, which means the steady state of TCP, quote unquote, is really increasing the congestion window until loss occurs and then halving the congestion window or reducing it multiplicatively. What that means is reflected in the equation below there, which says the achievable bandwidth varies inversely with the round-trip time of the network, meaning the longer the latency, the harder it is to get bandwidth, and also related to the square root of the probability of loss and the maximum segment size multiplied by some constant. What the key message there is that TCP suffers as latency grows, and that is a critical factor in the ability to distribute applications across the cloud. So you can, the ability to really take advantage of virtual, location-free, elastic resources is hampered by this the performance of network protocols. One thing that we do to mitigate that is a project in my group called Phoebus, which tries to bridge the performance gap that says as networks get faster, applications using the network get a little faster, but not as but they are not commensurately getting faster with the speeds of the network infrastructure. So Phoebus is trying to bridge this gap It's based on the concept of a session, which is layer 5 in the OSI protocol model, which folks learned about in their networking classes and then promptly forgot since it's not widely deployed in the internet. We've taken that idea and applied it to this data transfer, data accelerator service that allows adaptation points in the network to be composed into an end-to-end path. This dovetails well with cloud computing in that you can allocate these data helpers on demand for a given instantiation of infrastructure. They can improve the performance dramatically. We had some experiments with Amazon EC2 and a visualization application running across Internet 2 that showed that the use of Phoebus was able to improve the performance by 300%, for instance. I've resisted the urge to show a number of performance graphs, just trying to hit the high points here. Phoebus also provides a gateway for legacy applications. In a meeting here at the Internet Engineering Task Force yesterday, it was stated, one thing we've learned is that you can't touch the application. We need to be able to do interesting things in the network, but if we have to ask everyone on one day, on a flag day, to change the way they use the sockets API, for instance, it'll never happen. It won't happen. So the Phoebus project provides a gateway for existing applications they can run without modification and take advantage of this potentially dynamically instantiated infrastructure. We have a prototype deployed in Internet 2. You can see here the 9 POPs, points of presence, where Internet 2 has large-scale routers. Internet 2 is the network that connects the research, the universities and research institutions in the U.S. And we have Phoebus devices plugged in there, and we are, so a brief pitch, we are interested in having users evaluate this, and cloud computing applications are an excellent match for this sort of technology, and if you're interested in experimenting with this, we're happy to help you, so please be in touch.